introduce Christophe Poquet from the University of Lyon, and he will now talk about slow fast dynamics and periodic behavior in mean-field systems.
Okay, so thanks a lot for the invitation. So I'm very pleased to give this talk. And I will speak about research works that I did with Eric Luçon, it's written here, who is in Paris. So I will talk about mean field dynamics. So it will be a population of units that evolve with mean field interaction. And I will focus on periodic behavior for the systems. Okay, so let's first define the model I will talk about. So as I said, I will speak about a population of n interacting units in RD. So which means that I will be looking at n units that here define RD. So I will talk, there will be named xit, so t is the time. And for E, that is from 1 to n. And these units, we have the dynamics given by these three terms. So as a unit, you can think about, for example, particles. So which this free term will be first a blue term that is given by a function f, which will be a dynamic that is that belongs to the particle. So it means that if the unit is alone, it will just be evolve according to this dynamics. So you can imagine that it's some kind of potential that gives his evolution in time. Okay, but we have a population of these units, and so we suppose that there is also some interaction term, which is given in black here, which will be linear. That means that each unit will have wants to approach the mean of the whole population. That means that the term here is given by minus k, which will be, I spoke about this constant here, xi minus 1 over n, the sum of all the xj. So this is a mean field interaction because each unit will interact with the whole population, and there is no things about, we don't think about the position of each particle. There is no, the graph of interaction is very simple. It's a mean field that means that each unit will interact with every other unit with the same weight 1 over n. So that means that is why we speak about mean field interaction. Okay, so it's a term of interaction, and then we have noise. So each unit, we have its own Brownian motion. It will be standard Brownian motion that are independent. So you can think about population of particles that evolve in some space, or I will give an example afterward that will be of neurons. That means you can suppose that each neuron has a dynamics on its own that is given by some function f. So for example, I will give the FiztHugh Nagumo model, which is a model of neuron in 2 dimensions. So the f here is for the dynamics of each neuron, but then the neurons interact. There is this linear interaction term here. And you can suppose that this modelization with the function f is not perfect. So you added some noise that is for each neuron. Okay, so there is different parameters here in the system. There is this delta here that will be some positive parameter. And we'll speak, I will take this parameter rather small in the following. Then we have this term k, so we are in RD, so xa here is in RD. So k is a matrix, but for simplicity, we'll suppose that this is a matrix that is diagonal, with each term of the diagonal that is strictly positive. And then for the diffusion coefficients, again, B here is a Brownian motion in RD, and so sigma here is a matrix, but again, we'll suppose for simplicity that is diagonal with strictly positive terms in the diagonal. Okay, so I already said that the BA here is a Brownian motion, they are independent. And for the function f, we will suppose that it is smooth, so C with you can take every derivative you want. And we have some other assumption that is one-sided Lipschitz. So it's not Lipschitz, it's not that f of x minus s of y is smaller than the constant times x minus y. It's one-sided. That means that you have this kind of hypothesis, but for f of x minus f of y, a scalar x minus y. But again, it's more or less the same. It's in the same idea, but just you have this Lipschitz hypothesis in one direction. And we take this hypothesis so that we can have unicity of the solution for this equation. So existence and unicity with this kind of hypothesis for F smooth and one-sided Lipschitz is very classical. It's not a problem. Okay, so we want to look at this kind of population of units that evolve in time. And of course, if you want to take a lot of units and very large, but you want to study the dynamics of this kind of model, the idea is you want, for simplicity, to take the limit n going to infinity. Okay, and for this kind of model, it's something that is very classical. It was already studied in the 80s by Snitzman, Maxine, and by many people afterwards. For this kind of model, a good way of looking at this is considering the empirical measure. So what is the empirical measure? It's just 1 over n, the sum for I going from 1 to capital N, so the whole population, the Dirac at the position of each particle. So that means that when you look at this, you are looking at the evolution in time of some probability distribution, because you will normalize by 1 over n here. And this distribution looks at the position of the whole population. You just don't look at x1 or x2, but at the whole population. Okay? And so this is, see if you look at this in time, it's the evolution of some continuous trajectory that lives in the space of probability distribution. And if you suppose that at time 0 initially you have some convergence, so if you suppose that mu n0 converges weakly to some profile mu0, that can be smooth or anything, then what you can show, what I've shown in the 80s, is that if you look at some time interval that does not depend on capital N, so you fix some time interval 0 capital T, if you're looking at the empirical measure mu nt, then this profile and t converges weakly to this solution, to some deterministic solution. So it has, a deterministic solution, which is in fact the solution of the nonlinear Fokker-Planck equation that is written here. So let's just have a look at this PDE here. So I kept the colors here so that we can see the link between the terms in the initial particle system and the PDE. So in the particle system, we had this evolution term for each particle given by F, this interaction term, and the noise in red. In the limit for the empirical measure, you get back some term that is for the noise, but now the Brownian motion becomes this diffusion term, where you have again this diffusion coefficient. The term that gives the dynamics of each particle F, it's given by some Trossmann term here in blue. And you have the interaction, which is some nonlinear term. Why do I say it's nonlinear? Simply because you see mu t here and you see it again here. The other terms are linear. But again, you were looking at the beginning, you compare xy to the empirical mean of the particles or the units. At the limit, you get x minus the integral of z against mu t. Okay, so if you're looking at the limit for n going to infinity, you're looking at the empirical measure, you get some nonlinear PDE. But to understand a bit better what corresponds this PDE, in fact, this PDE gives the evolution time of the distribution of some Makin-Brazov process that I wrote here. So maybe you already know the linear Fokker-Planck equation. When you have a linear Fokker-Planck equations, it gives the evolution in time of the distribution of some diffusion process. Yeah? In which, if you have a Brownian motion, you have some Laplacian here, and the drift gives you some transport term. But when you have a nonlinear term, in your Fokker-Planck equation, it doesn't give the evolution of time of the distribution of a diffusion process, but of a Makin process. And this time, for this case, it is with these terms here. So mu t is the distribution of xt, which has three terms in its dynamics: the Brownian motion, a Brownian motion here, a terms given by the function f here, which gives the transport term here, and some interaction term, but this time you have the interaction between xt and the expectation of xt. So it's not a diffusion, because you have the distribution of xt appears in the dynamics of xt. So it's not a Markov process, this term, though it's called some Makin-Blazos process. And in fact, intuitively, if you're looking at the limit for n going to infinity of this dynamics here, if you are just looking at the dynamics of x1, in the limit, you want to write this equation. Why? Because you want to take here f of x1, a Brownian motion, and here in this interaction term, you want to say that, well, at the limits, all the xa will have more or less the same distribution, and so the empirical mean has to go to the expectation. So it's exactly the limit here. So in fact, it's intuitively what you want to write, and you can prove it's some classical results given by Smithman or Makin himself. He showed that, in fact, if you look at one particle at the limit, it follows this evolution. Okay, so we have a large population of units. If you're looking at the empirical measure, the limit is given by this evolution, this PD here with these three terms. And the question is, what can we say about the dynamics of this PD? So, and in fact, I will focus in this talk to cases in which I will try to prove that this PD here can have a periodic behavior. So of course, it will depend on the choice you make for your parameters, and in particular, in the choice on the function f here you're looking at. Okay. So what kind of units I want to look at for this problem? I want to look at excitable dynamics, excitable systems. So what do I mean by excitable systems? Sorry. It will be, so it's not really a mathematical definition of excitability. There is no rigorous definition of this kind of systems. So what I will say, how we define excitable systems, it's systems that possess a stable rest position and that have a threshold phenomenon. So the easiest way to understand this is to look at a very simple example. So dynamics defined on the circle given by this kind of model. So imagine you have some very simple dynamics on a circle in which you have some stable fixed point and some unstable fixed point. So what I say is that this kind of system is a very simple example of excitable dynamics. So in an excitable dynamics, I want to have a stable rest position. So in this case, it will be this fixed point here, this stable fixed point. So that means that when I start for the fixed point, I don't move. And when I move a little bit here, for example, I will go back quickly to the stable fixed point. So it's a stable rest position. And then I will have a threshold phenomenon in the sense that after a sufficiently large perturbation, I will have some complex trajectory before coming back to the stable rest position. So in this case, there is a threshold phenomenon simply because if I perturb a bit my initial position, so I start from here, but then I move my initial position to the left. If I go beyond the unstable fixed point, I will not come back directly to this one, but I will go around the circle before coming back. So in this case, it's a very simple example of complex trajectory before going back to the stable fixed point. So it's a very simple example, but you have some example in the real life. For example, a neuron, it's in some neurons are excitable system in the sense that you have some potential of the membrane of the neuron, which is stable. And if you perturb a bit this potential, it will go back to its first position. But then if you give a perturbation with a sufficient amplitude, then you will have some complex trajectory. It will be simply that the neuron emits a spike to its neighbors before coming back to its first position. So of course, it's a very more complex system than this very simple one, but in a sense, it's also an excitable system. Okay, and why are excitable systems interesting in the case of mean-field interaction? It's simply because it has been remarked that for noisy excitable systems, if you put them with mid-field interaction and you add also noise, then you can see you can observe some synchronized periodic behavior. So that means that you take units that on their own don't have any periodic behavior. So these simple dynamics here don't have any periodic behavior, but then you add some interaction. You consider a lot of excitable system. You make them interact. You add some noise. If you choose well the parameters, then you can observe some global periodic behavior. So it's something that is surprising. It's a periodic behavior given by noise and interaction, and it has been observed in many excitable systems. So this one, or also simple model of neurons. Okay, and so our aims when we were looking at this problem was, can we prove rigorously this kind of periodic behavior? Okay. So of course, if you want to look at this kind of problematic, the first things to do maybe is just to look at this simple model to add interaction and noise, and look at and ask if you are able to prove rigorously that you have periodic behavior from this kind of model. So it's something that was done. This kind of model was defined in the 80s by Kuramoto and Shinamoto from Japan, and indeed they consider the population of capital N oscillators. So this time the dynamics is defined on the unit circle, or not the unit, on the circle, and with dynamics again with three terms, where you have some dynamics for each phi that is given by some potential V, some interaction, and some noise. So again, the noises will be independent, just independent Brownian motion, standard Brownian motion. For the interaction, well, if you're not on the circle, you cannot take some linear interaction as we did before. You cannot just define minus k phi a minus the sum of the phi j. You cannot do this on the circle, but you can, for example, take k over n, the sum of sinus the difference of the phases. And if you take minus one here, the rotators will want to attract themselves. They will be attracted to the more or less the mean of the phases. Okay, and so we have to make a choice for this potential here. And you can take for a simple potential given by v of theta equal theta minus a cosinus theta. So if we take this kind of potential, this means that the derivative is just 1 plus a sinus theta. And the shape of this potential will depend on the coefficient a here you have here. And if you take A strictly positive but smaller than 1, then you have this kind of shape here, and you don't have any fixed point for the dynamics given by just, so here I'm just looking at the dynamics given by the potential here. So it means that dot theta equal minus v prime of theta. So for if you forget these two terms here, you just take this one. For a minus a smaller than 1, you don't have any fixed point. But then if you take a larger than 1, you have the two fixed points, a stable one and an unstable one. So you are exactly in the same situation as before. And so again, you can take the limit for capital N going to infinity. You're looking again at the empirical measure. So 1 over n, the sum of the position on each phi A. And this empirical measure converges weakly to the solution of a nonlinear Fokker-Plot equations, which is very similar to the previous one, where you have this Laplacian term, the Transmont term with the V prime, and some interaction term with this time an integral of sinus theta minus psi. Well, it's different because we took some different term for the interaction here. And so what Shinomoto and Kuramoto did in the 80s, they made numerical simulations, and they showed that indeed there were choices of parameters that mean choices of A and delta here, such that you had periodic behavior for the world population. And in fact, what we did in 2012, so it was myself and Jean-Baptiste Jacomin, Kashaya Pagdaman, and Xavier Pellegrin, is that we could prove that for this PDE, if you take delta, the parameter delta that is here small enough, you can prove that there is some limit cycle, so some periodic solution. Okay, and so I will not enter into the details here. So how we prove this? It uses the theory of normally hyperbolic manifold, because I will speak a bit more about this kind of concept in the following for the other systems. So, but we could prove that for this very simple system, you can have periodic behavior. So one unit doesn't have the periodic behavior, but you put interaction and noise. And for the whole population, you have a periodic behavior. Okay, so this was for dynamics on the circle. And now let us come back to a system in RD. And the question is, can we prove that there is periodic behavior for this system in RD? So a system a bit more complex. So what kind of function f do I propose you to take? The first one I would propose to take is, in fact, again, a very simple one that is more or less the equivalent of this one, but in R2. So how to get something that is more or less similar to this one? Well, we could propose a dynamics on RD, which has a stable fixed point and an unstable one that is close to the fixed point, to the stable one. So how you get this kind of dynamics? You can, for example, take f that is polynomial in R2 with, again, a parameter a and a parameter b. And if you take f that is equal to x squared minus a in the first component and minus b y in the second, what you get is that there are two situations, one for a negative and one for a positive. So for a negative, the trajectory just go to the right and tend to go to be attracted to the this axis here. But if you take a positive, you get two fixed points at the position x equal minus square root of a and plus square root of a, with a stable one that is here and an unstable one that is here. Okay, so you could say that there is nothing that is periodic here. Of course, with dynamics that is a polynomial, you cannot expect to get something that is periodic. But well, this model is similar to this one here, at least in the vicinity of the stable and unstable fixed point. That means the question here is, can we prove that with this kind of function f, with this interaction at noise, can we prove that for a big population, so in the limit of n going to infinity, there is a solution that is able to move to the right? That is, with A positive, just for 1 unit, you are stuck here at this stable fixed point. So are we able to prove that for the whole population is able, with the interaction at this noise, to go to the right, so to escape the stable fixed point? So it's a very simple example, and if you would like to have some periodic, so you could imagine that you take f that has this shape close to these points, and then you modify your function f so that once you have escaped from here, you go back, you turn around and go back. Well, but the idea is just here to look at the limit n going to infinity, and to prove that with a good choice of parameters, the whole population is able to escape this stable fixed point. Okay, so this is the first example in RD. And a second example is given by a classical model of neurons. So there are many ways of modeling the dynamics of a neuron, models that are more or less simple. So the FiztHugh Nagumo model is not very realistic model, because it's just in 2 dimensions. There are models that are more realistic, like this Huxley model, which is in 6 dimensions, for example. But it's a simple model in which you already have a lot of features that are that you can observe in the dynamics of neurons. So this model is given in 2 dimensions. So you have 2 terms, V and W. Here, V represents the potential of the neuron, and the dynamics of V is given by this term here. And W is some internal dynamics of the neuron that makes, when there is a spike, it's this term that makes it go back to the stable fixed point. Okay, so you have different parameters. So if it's a polynomial dynamics with some parameters, you have the parameter A here, B here, and C here. So when you move this parameter, you can have a lot of different dynamics. You can have fixed points, unstable fixed points. You can have one periodic solution. You can have 2 or 3 periodic solutions. So you have a lot of different dynamics that you can have when you play a bit with the parameters. So I will focus to 2 choices on parameters. I will take, for example, A equal to 1, B equal to 1/3, and C equal to 10. And in this case, you have just one stable fixed point. So these lines here are the null lines. So it's just the curve that make these 2 equations equal to 0. And of course, if you are looking at the intersection of these 2 curves, then f is equal to 0, and then you have a fixed point. But with this choice of parameters, in fact, this is a stable fixed point. Okay, so it's the first choice of parameters. But then if you move a bit the parameters A, for example, taking A equal to 0.7, then you still have a fixed point here, but it becomes unstable, and you have a periodic solution that is locally stable. And in this case, this model is excitable in the sense that if you are in this house, if you are close to this fixed point here, if you move a bit the dynamics, if you move a bit, the initial condition, you go beyond this curve here, we will turn, sorry, no, sorry. So this time, this system here is not excitable, of course, it's just periodic. So if you move a bit the initial condition from this red point here, will converge to the periodic behavior. But this one here is excitable. So it's not, you cannot see it just looking at my picture here. But what happens in this with this choice of parameter? So the first choice of the parameter is that if you move a bit your point, your initial condition from here, you will go very quickly. We come back to the fixed point. But then there is some kind of restore phenomena in the sense that if you go a bit further down here, for example, starting from here, we have some complex trajectory. That means that the system will first go to this direction, move around, and then converge to the fixed point. So it's another example of dynamics in R2. And in this case, with this choice of parameter, we are excitable. And again, the question is, if I just take one unit, so I forget the interaction and the noise, I just take the dynamics given by F, I don't have anything periodic, I just have a fixed point. The question is, can we prove for this model, if we consider interaction and noise in the limit of large population, can we prove that for the PD, we have something that is periodic? Okay, so that's the aim of this talk. And of course, let me just talk a bit about what are the work that had already been done in these directions. So there are people that were already interested in the existence of periodic solutions for nonlinear focal point equations. In fact, the first one who showed that this is possible for nonlinear focal point equation is Michael Schutzoff, who gave examples of periodic solution of nonlinear focal point equation with periodic solutions. And other people did it also in 2012. And the idea followed by Schutzoff at the beginning, what he did is looking at particular nonlinear focal point equation for which you have Gaussian solutions. And so if you have Gaussian solutions, if you know that if we start from Gaussian solution, it will be a stay Gaussian, you just have to look at the expectation and the variance of your solution. And if you can show that you have something periodic for the dynamics of the expectation of the variance, then you can show that you have periodic solution. So it's what he did in the 1985. And then he showed that for some a system of interacting units that is the oscillator that is coming for chemistry, he managed to show that he had some periodic behavior also in this system. Okay, so that's for the nonlinear focal point equations, and more precisely for the FiztHugh Nagumo model, so the last one I described. Some people looked at this model recently in the 2016 and 2008, but they looked at some model that is a bit different. They call it kinetic midfield of FiztHugh Nagumo model. It means that, in fact, here I put noise in the both coordinates. They looked at the system in which you had only noise on the first coordinate and not on the second. So that's why they called it kinetic midfield FiztHugh Nagumo model. And they showed that for this model, if you have a small coupling, you put noise interaction, but a small term for the interaction, then you have a stationary solution and stability for small coupling. So you don't have any periodic behavior. And what they showed also is that if you take now a very large coupling at the limit of the coupling going to infinity, then you get back the FiztHugh Nagumo dynamics for just one unit. And so if you had something periodic at the beginning for one unit, you get back something periodic for the PD. Okay, so I will talk about things a bit different here. For what we did, we took a coupling that is not too large and not too small. also some noise that is not too large and not too small. And what we will do is a bit different. We'll go take the parameter delta going to 0. We'll take k and sigma fixed. What they did is they played a bit with k. We'll take k and sigma fixed, but we'll take delta going to 0. Okay, so that is for the FiztHugh Nagumo model, and also for other models of neurons. There are also work of mean field dynamics, but with different systems. There are also models of neurons with jumps, but with midfield interaction. And also people show that for good shows of parameters, you can also have periodic behavior for this kind of models. Okay, so let's go back to our system. So recall that if we take the limit capital N going to infinity, what you have is this nonlinear PDE, nonlinear Fokker-Planck equation, nonlinear because here you have mu t that appears 2 times here, and which is the distribution of this process here, which is not a diffusion, it's not a Markov process because you have the expectation, so the distribution of xt appears in the dynamics of xt. Okay. So how can we prove that we have some periodic behavior for this kind of PDE? So what we do is we will look at the system as a slow-fast dynamics. So maybe it's not very clear why this system here can be seen as a slow-fast system when delta goes to 0. So to see this property, let's make some kind of change of variable. So instead of looking at the dynamics of mu t, we'll look at the dynamics of mt. So mt will be the expectation of xt. And on one side, we look at mt, and then we look at pt, which is the distribution of the recentered process, so xt minus mt. So if you look at these two quantities, so you don't have just one PD, but a system of equation with one differential equation for MT and one PD for the evolution of the distribution PT, which is the distribution of xt minus MT. So for the first one, it's quite simple. If you are interested in the dynamics of the expectation of xt, you just have to take the expectation of this equation here. And so what happens when you take the expectation of this term here? You take the expectation of f of xt, okay? Then if you take the expectation of this term, you get expectation of xt minus expectation of xt. So this term simply disappears. And the expectation of the Brown motion also disappears. So you just have, when you take the expectation of the first term here in blue. So if it's expectation of f of xt, but then if you want to express it in terms of mt and pt, it's just the integral of f against pt, but since it's the recenter distribution of xt, you have to take f of x plus mt. You have to make this translation here. So the dynamics of mt is really simple, it's just this blue term here. And for the dynamics of pt, well, you have just to make a change of variables here, and you get 3 terms. You get just it doesn't change anything for the Laplacian here. For the term of interaction, since you recenter the process, you don't have this recentering here. You just have the gradient of pt kx, so this term disappears. And then again, you get this transport term, but you have to make this translation by the mt in f here. And don't forget, since you make this translation of mt here, when you take the derivative, there is also dot mt that appears. So it's a simple calculation. And so you can define the evolution of mt and pt, and it's something that is closed in mt and pt. So what is why do I make this change of variable? But, well, now we can see that is some slow fast system. Why? Because if you take delta going to 0, what happens is that the dynamics of mt becomes very slow because delta goes to 0, so this term here goes to 0. So this term is a slow term, so MT is a slow variable. And if you look at the second one, MT is small, dot MT is small here, you have delta here, so the blue term here is small, but these two terms do not depend on delta directly. So this term, PT, is a fast variable. So MT is a slow variable, PT is a fast variable. Okay, so making this changeable variable, you can see that you have some slow fast dynamics. Of course, the miracle here is that we took something that is linear from the interaction, so that this term here disappears. Okay, so it's a slow fast system. And if you want to look at the dynamics of a slow fast system, the first thing to do is to understand what happens when delta is small, and even when delta is equal to 0. So what happens when delta is equal to 0? You get a system that is quite simple. When delta is equal to 0, the blue terms here disappear. And so you just have MT equal to 0 and the derivative of PT that is equal to this PD here, where the blue term disappeared. Okay, and now maybe you recognize some very classical process here. So now this PD becomes linear, the blue term disappeared. And in fact, PT is just the distribution of the Ornstein-Uhlenbeck process. So which is given by dxt equal to minus kxt plus square root of 2 sigma dbt. So it's a very simple process. I think everybody knows. So you can say a lot of things about this process. If you start from something that is Gaussian, you stay Gaussian. You can show that it converges in distribution to some normal distribution that is in fact with mean 0 and variance sigma 2 k minus 1. And you can prove that it's converging in distribution, so you can express this in many different ways, in Wasserstein distance, etc. So you can also say that if you look at PT, so PT, the distribution of this process, you compare it to Q, which is the limit, so this normal distribution with these parameters. If you look at it in some weighted L2 distribution, weighted L2 norm, sorry, then this converges exponentially fast to 0. So it's smaller than exponential minus the minimum of the terms of the matrix K is times T times the initial condition here. Okay, so when delta is equal to 0, what you have is the expectation MT, which does not move, sorry, and the recentered distribution that goes quickly to Q. So this is for delta equal to 0. So intuitively, the approximation you want to make for delta small, well, what happens? If you imagine that the fast variable goes quickly to Q, you want to say, okay, so at first approximation, I want to say that PT will be more or less equal to Q because it's attracted very fast to Q. And now for the dynamics of MT, well, the dynamics of MT was given by this term here, but if you say that PT is very close to Q, you want to replace it at first approximation by Q here. So what you want to say that at first approximation, the dynamics of MT is just given by the integral of f of x plus MT, again Q. And in fact, it's just a function, Q doesn't move here, so it's just some function of MT. A function f, which is not equal to f here, it's some modified function f, which depends on the parameter sigma quads k minus 1. And what does it mean? What is this approximation? More precisely, in fact, if you make this approximation, you are saying that the recenter distribution doesn't move and stays Gaussian, and the expectation moves according to this term here. So that means that you make the approximation ut is more or less equal to a Gaussian centered at MT with this variance here, variance matrix here, and with dynamics given by this term here. And making this approximation, of course, it's an approximation. You have to show that you can make this approximation. But this approximation is a really simplifies a lot your problem, because you started with trying to look at periodic solutions for a PD, so in an infinite dimensional dynamics. And now you are just looking at the dynamics of the expectation, so it's a d-dimensional dynamics. Okay, so, well, I'm not very quick. So what I will just show now is, okay, I have this approximation. So is this approximation interesting for the two examples I gave before? And in a few words, how can you make this approximation rigorous? How can you prove that in fact, you can make this approximation? So let's go back to our two examples. So recall that you have the reduction, this approximation. We say that mu t, the solution of my PD, is more or less equal to this Gaussian with these parameters, and the dynamics of MT given by this modified function f. Okay, so for my first example, we will recall this simple example that was given by this polynomial function f in R2. Well, what you are doing, so if you want to look at this approximation for this model, you have to compute this modified function f. But this modified function f, what is it? It's just an integral of f of x plus mt against a Gaussian distribution. So in fact, if f here is just a polynomial function, you are just looking at moments of your normal distribution here, Gaussian distribution. So in fact, for a simple function as this one, you can compute explicitly the modified function f. And for this example, the modified function f at mx and my is just given by this function here, in which you recognize more or less the initial function f. So it's the same function with just some shift in the constant a here. Okay, so now we call that this was the functions for just one unit. So for one unit, if you suppose that you are in this situation, so with a positive, one unit gets stuck in the stable fixed point here. But now, if you believe in my approximation for the whole population with interaction and noise, if we take the interaction sigma 1, so it's the noise of the first coordinate and the interaction of the first coordinate, so that this term here becomes negative, even if A is positive, then for the whole population, you are in this situation. So that means that the whole population manages to go to the right and so to escape the fixed point. Okay, so for this parameter, we are showing that if you believe in my approximation, you have a behavior for the whole population that is very different for the behavior of just one isolated unit. Okay, so they would manage to escape, but still, since my example is very simple, you don't have any periodic behavior. But let's look at my second example. So it's the FiztHugh Nagumo model. So recall it was given in 2 dimensions with this polynomial function f here. And again, since it's a polynomial function, you can compute explicitly the modified function f for the whole population. And again, so it's not in V and W, but it's in MV, MW, since you are looking at the evolution of the mean of the population. But again, it's more or less the same system, the same function as this one. It's just that against V here you have a 1, and against MV you have 1 minus sigma 1 squared over K1. So what happens for the system? So if you are looking at one unit given with the parameters A, B, and C, such that you are in this situation in which you just have one fixed point. So if now you are looking at the whole population, and if you believe in my approximation, then the dynamics of the mean should be given by this thing here. And so what happens when you take this red term, sorry, that is larger and larger? It happens that if you take this red term equal to 0.0866, what you get is that you still have this fixed point, but then you have a blue curve here, which is a stable periodic solution. And then if you take a larger parameter, 0.2, then the stable fixed point here collapses with this red curve, which is also a periodic solution, but that is unstable, and you get an unstable fixed point and a stable periodic solution. And again, if you take larger parameters, at the end, this periodic solution shrinks and collides with the blue point. At the end, again, you just have a stable fixed point. So this is the dynamics for the approximation for the mean of the whole population. And it shows that if you choose parameters for the noise and interaction that are, in a sense, not too large, but not too strong. So that means that if you fix, for example, the interaction, you take the noise that is large enough, but not too large, then for the whole population, you get something that is periodic. Okay? And so let me just show you some simulation of this model. So it's the simulation of a large population of FiztHugh Nagumo units with the parameters given in the slide before, and I took sigma square 1 equal to 0.1 and k1 equal to 1. So we were in the third case in which you have one stable, unstable fixed point and one periodic behavior. And what you see is that, so it's an histogram of the different units. And what you see is that, in fact, the units synchronize. So they tend to be more or less in the same position, but of course you have noise, so they are not in the same position. There is some diffusion around this position. But the whole population, the mean of the whole population follows the solution. So in black here, it's the periodic solution of my modified function f. Okay, so I still have, well, a few minutes. So with these two examples, I tried to show you that, in fact, this approximation is interesting for these models. It gives a good result if you believe in the approximation. So let me just say in a few words how we can prove that this approximation is in fact rigorous. So I will take one more hypothesis is that f is bounded. So unfortunately, for my two examples before, f was not bounded, so you have to modify a bit your system here to put some cutoff, for example, to have f bounded. But if I take f bounded, then I can prove that this approximation is good. So what do you want to prove when you want to show that it's a rigorous approximation? You want to get so we want to show that in fact you have a limit cycle for your limit PD, for your Fokker-Planck PD. So what is a limit cycle or in a stable periodic solution? So imagine that this is the solution of your PD. It's a solution that is periodic, so it's a closed curve. And if you want stability, it means that at each point of your curve, you can define some hyperplan here that you can call x0s, which are stable around the linearization of the dynamics or the differentiation of the dynamics with respect to the initial condition. So you differentiate your dynamics with respect to the initial condition. This is something that will let your flow, your hyperplane stable. So this hyperplane will be sent to this one by this linearized dynamics. And you want that the linearized dynamics is a contraction. So that means that you will, the linearized dynamics after one turn will make the point contracts toward the periodic solution. So that is a a stable periodic solution. So that is what you want to have for your PD. And in fact, with this slow fast framework, we don't really have this, but you are not so far from it. This means that since you have this modified function that has a periodic solution, what you can show is that you have a curve. You cannot directly show that you have a curve that is a solution that is closed, but you can show that you have a solution that starts, for example, for here, and that comes back not directly here, but that comes back not too far from your starting point. So with our slow fast framework, we are able to show that you are not so far, from having a periodic solution. And in terms of stability, we are also not so far, which means that you can define some hyperplanes here that are not stable under the linearized dynamics. But if you project the linearized dynamics on these hyperplanes, then you get a contraction. So you're not so far from having a stable periodic solution. And in fact, this kind of model, so you have some other hypotheses to verify, but it's what is called an approximately normally hyperbolic manifold by Bates-Luzeng. They define this kind of things in 2008. And what they showed is that, in fact, if you have this kind of approximate normally hyperbolic manifold, in fact, so it's a very deep theorem, they showed that you have a real normally hyperbolic manifold close to this. So in our case, this means that, in fact, you have this almost periodic solution with their deep results. It shows that you have, in fact, a real periodic solution. And so what we did with Eric Luçon is to show that, in fact, we are in the framework of the results. We can apply the results. And we showed that with this hypothesis, in fact, we have a periodic solution that is stable. And even you can show that it has an isochron map. So that means that, in fact, you have a periodic solution, and you can define a phase in this periodic solution, and you can also define a phase in the neighborhood. That means that point starting from here, you can define its phase, and starting from here, the solution, we go toward the periodic solution, and we be attracted to the point which has the same phase. Okay, and so we did it for F smooth and bounded. So it's a restriction with comparing to our examples from before here, which were with F, which was not bounded. But in fact, if you take unbounded function F and you have some more hypotheses, but hypotheses that are, for example, satisfied by the FiztHugh Nagumo model, you can also, with different tactics, but also linked with normally hyperbolic manifolds, you can show that you have a periodic solution. So we did this with Eric, but we had to prove this more by hand, and we didn't have this nice stability structure with the hypothesis of F unbounded. And if you take F bounded, then you can use this very strong result, and you have all the stability results that come with. Okay, so maybe I will stop here. I add some more things, but maybe I will stop here.
Okay, thank you very much, Christophe. Is there any question in the room, in the Zoom? Let me check. No question. So I wanted to ask if we may quantify how close this remains. So the empirical measure remains close to the periodic orbit. Do you have some norms, estimates on the distance between?
You mean so is it in the limits n equal to infinity or
Yes,
n,
yes. Yeah.
So it's something that is in the neighborhood of the system. So you can show that there is some periodic solution close to this one. So this one that is almost periodic, you construct it by hand. And there is a real periodic solution that is in the vicinity, that is of order delta of this one. And you have this in so we worked for this. You can choose the different frameworks, but we worked in Sobolev spaces. So
Okay,
to
so
do this, we took some Sobolev space that is with negative exponents and with some weight that is linked with the normal solution. So you can, in fact, you can also work in L2 or in Sobolev spaces with positive exponents. But what he had in mind is the result I didn't have time to speak about. But then this is for the limit and equal infinity. But then you want to compare the real empirical measure to this one.
Yes, in fact, this was my question.
You need some space in which you can define probability distributions, and when you take R large enough, depending on the dimension, you can do it.
Okay. Thank you very much. So if there is no question, then see you next week. Bye.
Okay. So
thank you, Christophe.